is not only on Earth or on the surface of a planet, it's also in outer space. It pulls things together. So, what gravity does, like, even when like it's a ball is falling down, it's attracting the it is attra- is attracting the ball towards the Earth. So, like, let me give you a visual representation. So the ball is getting attracted towards the center of Earth. But say if we're outside of like the Earth's gravitational sphere field, like say if this is orbit, right? We can we can no longer use this anymore. So this is why Newton was able to derive another equation, which is F equals big G times mass 1 times mass 2 over r squared. So mass mass 1 and mass 2 are just the masses of like the source and like the object that's orbiting that source. So like say if this is the sun and then this is the earth, those would be the two masses that would be included in this equation. R is the distance between their centers. So this distance right here is R. And G is just a constant that most ratios use, and that is 6.67 times 10 to the negative 11th. So this gravitational constant applies to all things in the solar system. So it's good to memorize it. So we can use both of these to describe attraction between sources. So recall that mm, orbits move in a circular path, right? Like this, right? Because it moves in a circular path, it must have a force from keeping it from moving in one direction. Therefore, it must have some sort of centripetal force. And because that planet that's orbiting like the bigger planet or the source is being attracted to the center, we can say that the force of gravity is a centripetal force. And because it's a centripetal force, we can use our equation, the centripetal force equals mass 1, which is the mass that or the mass that is the mass that is moving or being the one that's moving a circle path times v squared over r. And then we can set that equal to this equation right here. So mv squared equals g m1 m2 over r squared. So yeah, and then there should be an r here. So what we can actually do is, because these two are equal to each other, So m1g, again, this is the object that is orbiting the source, equals g m1 m2 over r squared. We see that these masses cancel out, so we get a pretty good approximation of the gravitational field. And also, what we can do is we can actually find other things like the period. Like, if we just have our centripetal force set equal to the law of gravitation, 1v squared over r. So we recall that v equals 2 pi r over t. So what I will do is we can cancel these out first. So g m2 over r squared equals v squared over r. So what I can do is I can sub this in for velocity. So g m2 over r squared equals 4 pi squared r squared over t squared over r. So we see here that basically we can cancel one of these r's out, so we get g m2 r squared equals 4 pi squared r over t squared and then what I'm going to do is I'm going to multiply r squared on both sides. So let me just, so g m2 over r squared equals 4 pi squared r t squared. So I'm going to multiply r on both sides, so I get g m2 equals 4 pi squared r cubed over t squared, and then I'm gonna divide by 4 pi squared, so I get g m2 over 4 pi squared equals r cubed over t squared. And all I'm going to do is I'm actually going to raise both of these to the negative first. So then we get 4 pi squared over g m2 equals t squared over r cubed. So if we look at the left side right here, in most orbits, the source mass 2, basically the bigger planet that attracts the smaller planets or like satellites or and all that stuff, that's mostly likely going to be constant because you're most likely not going to have a mass change. So we can presume this as a constant because all the planets orbit around this source, like the sun. The sun's mass is always going to be constant as it's in the center of the universe. But and because it's also it doesn't orbit anything else, so it doesn't have a certain it doesn't have a period, if that makes sense. Um, and then we know 4 pi squared is a constant, and then we know g is a constant. So t squared over r cubed is just equal to some constant, which means that this here is a ratio, and ratios are proportional. So say if you have 2/3 equals 4/6, they're both equal to some constant, but different numbers that you can simplify them and such. So basically, since this is proportional to a constant, we can say that t squared over r cubed, that's not cubed, that is a subscript, equals t squared over r cubed. And let's call this t1, r1, t2, r2. Because this value equals a constant, you can basically set up proportions for to have certain ratios equal to each other. And then this is known as one of Kepler's laws. So yeah, this is very good to know when you're given two planets that are orbiting like the sun, and then you're given like the periods or the radius, and you can